Hello and welcome to the Oral History Project at Cornell. I'm Bruce Ganem, Professor of Chemistry in the Department of Chemistry and Chemical Biology at Cornell. It's my privilege to be here today, October 15th, 2011, with my colleague and friend, Jerrold Meinwald, Goldwin Smith Emeritus Professor of Chemistry. I'm hoping our conversation this morning will touch on many of the highlights of Jerry's long and distinguished career here at Cornell in teaching and research. That career began almost 60 years ago, at the end of this year. And I've known Jerry for a long part of that time, almost 40 years. So it's a particular pleasure to reminisce with him on the record, as it were, about the many contributions he's made to chemistry and to Cornell. As most of you know, Professor Meinwald is an internationally known and distinguished organic chemist whose achievements have been recognized by many awards. He's a member of the National Academy of Sciences and the American Academy of Sciences, as well as the American Academy of Arts and Sciences, I should say, and the American Philosophical Society. In addition, he is one of the co-founders, along with the late Professor Tom Eisner, of the modern field of chemical ecology, which, as we all know, is the study of how chemicals mediate interactions between living organisms. Good morning, Jerry.
Good morning.
It's a great pleasure to be here with you, and I'm hoping we can start our conversation early on with some background to your childhood and family life in New York.
Okay. Yeah, my interest in chemistry actually goes all the way back to my boyhood. Mm-hmm. And I had a friend, Michael Cava, when we would get together during summers on the beach. Michael Cava's father was a physician, and in his office there were biochemistry books and chemistry books from his student days. And Michael somehow got interested in those, and then got me interested in those, and would say things, look, you can make these wonderful red crystals out of blood, and isn't that remarkable? And so we would lie around on the beach and talk about the role of chemistry in life. Mm-hmm. And that finally led to us starting to do some chemistry, just for the fun of it, and not with commercial chemistry sets, but with things we could buy from drugstores or supply houses. And we graduated quickly from biochemistry to fireworks.
It's amazing you could buy stuff like that in stores at the time.
At that time, children could buy anything that they had the money for.
So you would go out on the beach and construct elaborate fireworks
we would
and
construct
set them off?
Fireworks, and we would charge the neighbors 5 cents each, and we would put on fireworks shows in the evening, and they were quite exciting.
Yeah. What a great companion. Of course, Mike went on to become a terrific organic chemist in his own right, and here you two were in the very beginnings of your career as friends.
Indeed, and we got excited about it and stayed excited the rest of our lives.
Yeah. So this was early on as high school students, even grade school students?
Actually, I think we were probably in junior high at that time. It was well before high school. Mm-hmm. And it's interesting. So we graduated to the stage of, we both grew up in New York City, of using the great 42nd Street Public Library, where we would go on Saturdays with our notebooks, hand copy procedures for synthesizing dyes. We learned at an early stage that you need to learn German.
That's
because
right.
a lot of that literature
it was early German chemistry.
It's in German.
Yeah.
And that was a very good motivation. Actually, when I finally came to Cornell, I noticed that Cornell required chemistry majors to take German.
Yep.
That has changed enormously since that time.
We all had to study German as graduate students, certainly,
right.
if not sooner. Yeah. So there you were in New York, and it came time to move on to college. You and Mike parted ways at that time?
Yes. So Mike went off to Harvard. I didn't get into Harvard. So I went off to Brooklyn College and started studying there, and then the family moved to Queens. I moved to Queens College. After a year and a half of that, I turned 18, and World War II was still going on.
Right.
So I was drafted, and managed to get myself into the Navy, which I was very eager to do because they had a program for training electronics technicians, and it seemed to me that would be a good activity. I couldn't imagine actually being in battles, but I could imagine doing electronics. And so Mike was was still in college. I was spent a year and a half being in the Navy.
So there was a quick stint in electronics school and then working
actually
around
it was the training was about 9 months. And then I was on a hospital ship called the Constellation. And we sailed to Panama, and we sailed to Guantanamo, and we sailed to various interesting places. And then finally the war was over. I spent only 18 months. And when I came out, I transferred to University of Chicago.
There was the GI Bill, of
So
course.
there was the GI Bill, and the atmosphere in Chicago was different from the atmosphere in Queens College. It was a more cosmopolitan student body, very sophisticated faculty, and that was a great place to finish my undergraduate work.
So tell us, who were the organic chemists at Chicago at the time?
Organic chemists at Chicago at the time were George Wieland, who had been a student of Linus Pauling and was an important person. Frank Westheimer was on the faculty.
He would have been quite young then, huh?
Who would have been a young Frank Westheimer. Henry Tauby was on the faculty, who spent a short time at Cornell.
That's correct,
It was a very lively faculty and a wonderful place to be an undergrad.
So did undergraduates work on research projects then, and were you in anybody's lab?
Actually, I was not. So I think maybe undergraduate research was not such a common part of the experience at that time. But I got very good advice. I remember talking with George Wieland about where to go to graduate school, and he said, well, if you're interested in organic chemistry and synthesis, then probably you should consider Harvard and working with R.B. Woodward.
That was good advice.
That was good advice. And Mike Kava gave me the same advice, and I managed to do that. That was very exciting.
So you went off to Harvard in late 40s,
so
48
I went off to
maybe?
Harvard in 1948.
Okay.
Joined the Woodward Research Group almost immediately. And again, that was a quite different experience than being at Chicago, because the kind of chemistry that the faculty was interested in was different.
Right. So Woodward himself would have also been a pretty young, obviously very dynamic faculty.
Actually we're just 10 years apart. I think Woodward was born in 1917, and I was born in 27. But he was a well-established figure by then because he got a very young start. And so he had already synthesized quinine. He'd been on the cover of Life magazine and whatnot, and was the young star of the department.
So he must have had a pretty good-sized research group.
And he probably had about 20 people working with him.
Postdocs and students?
And postdocs and students. Indeed,
So what was that like? Tell us about your project and what life was like in the Woodward group. I'm sure there were many good people there.
Was very valuable and pleasant. Woodward was a great research director. It's interesting, he had two different directing styles. The directing style for his postdocs is he made them into small teams, 2 or 3 or 4 people with a ambitious objective, and he would consult with those researchers essentially every day. How did this reaction go? Has this thing crystallized? Show me what's going on.
Very detail oriented.
Very detailed direction. And he would come in maybe around 9:30 or 10 in the morning, and go home about 11 or 12 at night. Put in a it started a little bit late, but a very long day. And so that was working with the postdocs. Working with the grad students was a quite different experience. We had individual projects. I was working on the synthesis of lysergic acid, which is the key central structural core of the ergot alkaloids. And students had individual projects. I didn't have a team. I was by myself. Woodward had proposed how we might approach that synthesis. And essentially, he let students work on their own. you would try the next reaction, and if it worked, you would go and do the next step. If you were having troubles, you go to his office and say, this isn't working out right, and then he would analyze what did happen, what are we going to do about it, how are we going to improve the conditions or change the strategy, and you'd go back all fired up. Woodward could think of an infinite number of ideas, literally, to get around any problem. I remember going back to the postdocs. I had a very good friend, Franz Sondheimer, who was working on total synthesis of cholesterol. And there was some stage, it was just a simple Michael addition to acrylonitrile. And Franz would try it, and it wouldn't work, and they'd go talk about it, and he'd try it again. And Woodward got him to try at least 50 different approaches to that single
to the Michael reaction.
And it worked, finally. But most of us don't develop that tenacity. You try something 5 or 6 times, you don't have new ideas. To have new ideas for that long, and to convince your coworker that this time it's going to work, so let's go do it, was a remarkable feature of Woodward research direction.
So he could inspire you, right? He could
really
inspire you to keep trying things.
And the other thing is, he knew the literature in a way that I don't think anybody knows the literature these days. So he could cite analogies and direct you to them without looking them up. Go look at in the British Chemical Journal, and I think it's 1952, and it might be page 823, and then a paper by Lord Todd, and that has something useful for you. And so you go to the library, and there, literally, there it
to
was.
the page, accurate to the page.
Just as he said. So it's interesting, because on the one hand, that's inspiring. On the other hand, you do realize that however hard you work, you're not going to reach that level of intimacy with your subject. It's just, it's beyond imagination.
But if you look at the constellation of people who succeeded from Woodward's group, it's clear that the inspiration was much more than any intimidation by his intellect. He had a way of motivating people, I guess.
Yes, he really did. And clearly he enjoyed the process, and he got you to enjoy the process. And also, he felt that he was absolutely in the forefront of the subject, and he got his coworkers to feel they are bringing forward organic chemistry.
So, Jerry, you mentioned Franz Sondheimer, and I think Mike Cava was still there when you were there. Who can give us a feeling of who else was in the lab at the time? There must have been many other well-known organic
There
chemists.
were many well-known. Ernie Wenkert was there in the Woodward group. There were, of course, other distinguished research groups. So in Louis Fieser's group, there was Koji Nakanishi. In Gilbert Stork's group, there was Jean Van Tamlin, Al Bergstaller. There were very, very good people in all of the groups. And so the general atmosphere, especially for organic chemistry, was really lively.
And who were your closest friends and buddies, the people you would talk to about Michael reactions and other
Yes, I think my closest friend was Franz Sondheimer. We had adjacent lab desks, and we shared an interest in music. We would go to concerts together and whatnot. But mostly we spent pretty much the Woodwardian hours, as we came in a little bit late and worked into the night.
Yeah, we should talk a little bit about music, since it was a passion of yours since your early days in New York City. Mike Cava played an instrument?
Mike Cava actually played trombone, and Mike and I used to play duets in our early school days. We would play duets while the reaction mixes were refluxing, and that got a little more sophisticated. By the time I was in Harvard, I was studying flute with James Papoutsakis, who was the second flute in the Boston Symphony. And then a subsequent year, my childhood hero, whose name is Marcel Moïse, who was the world's great flutist. Marcel Moïse was teaching flute in Boston one day a week, and I began studying flute with him. So actually there was a time when I actually realized I was studying flute with the world's greatest flutist, and I was studying chemistry with
the world's
who you could
greatest
actually
organic
consider the
chemist.
world's greatest organic chemist. After that, everything is downhill. But that was a wonderful time.
Wow. And you made time to do all these things somehow.
Yes. Well, again, I took the flute to the lab.
Yeah.
And again, there were times when you had an hour and nothing much was doing, and
Mhm.
when one could play flute.
Mm-hmm.
Yeah, I used to play flute and clarinet duets with a man called Frank Weisenborn, who went on, I think, became research director of Squibb later
Mhm.
on. And Weisenborn was a very good clarinetist. And we played a lot of
Yeah.
music in off hours.
Yeah. Did Sondheimer play anything?
No, Sondheimer
He just enjoyed
loved
listening,
music
yeah.
and knew music very well,
Yeah.
but didn't play.
So those were great times at Harvard by
So
now.
those were great times.
And then it became time to leave.
Yeah. So as I was sort of rolling along, working on lysergic acid,
Mhm.
but not quite getting there, the senior organic chemist at Cornell, who was Jack Johnson, wrote to the chair of chemistry at Harvard, who was
Mhm.
Paul D. Bartlett,
Right.
and said, "We have a faculty opening, and might there be somebody at Cornell who we should be looking at?" And Bartlett passed this lecture around, this letter around, and Gilbert Stork, whose office was right next to my lab, came in one night and said, "Jerry, there's a job in Cornell,
Mm-hmm.
and you probably should apply for that," which put me in a really strange position because, of course, I was working with Woodward and
Right.
not Gilbert.
Right.
And finally I decided I would go approach Woodward, and I said, "Well, Professor Stork tells me there's an opening at Cornell, and would it make any sense for me to look into that?" And Woodward thought for a minute and said, "Yeah, that's a very nice idea.
Wow.
Why don't we write
Mhm.
and see if that would work out?" And which it ultimately did. If we
Mhm.
condense that story,
Yeah.
it did. And in fact, I hadn't even quite finished my thesis, so I came here in January 1952.
Mhm.
Hadn't quite completed the synthesis, but one could write a thesis on what I had done.
Yeah.
And that actually reveals something also about Woodward's attitude towards graduate training. And Woodward's feeling with postdocs was they are going to make cortisone, or they're going
Mhm.
to make vitamin B12.
Mhm.
His attitude with students is he's training them, and you pursue your problem, and when you come to the stage that you do an experiment, it gives results, you analyze the results, figure out what to do next and do it. When you can sort of do that cycle
Mhm.
reliably, then you're ready to go.
So he taught you
And-
how to do research.
And so he taught, that's right, so it was sort of the approach to how do you do the
Yeah,
problem.
yeah.
And he wasn't really expecting that every student would complete the target that they were aiming
Yeah,
at.
yeah.
And in fact, I think if one analyzes Woodward publications, one will find that they're mostly with the postdoctoral students.
Right.
They're sometimes not with graduate
Yeah,
students
yeah.
at all, who maybe didn't finish their lysergic acid,
Mhm. Mhm.
but they were ready to go in his eye, and he was happy to see them go off and start. He thought it's more important to start your independent career than to spend another 2 years to get that last step to work.
So I'm curious to know whether, before we leave this subject, whether much was known about the properties of lysergic acid when you were working on it.
Well, it was a time when LSD just
So it was known.
So it
Okay.
was known that the ergot alkaloids have bona fide pharmacological uses, and aside from that, there was the business of hallucinogenic drugs and
Yeah.
whatnot, and
Okay.
yeah, and that was all known.
Okay.
Woodward tended to pick targets that would bring renown to the department,
Mhm.
to his own efforts,
Sure.
when he solved them.
So you came to Cornell and it was winter of 1952.
It was winter of 1952, and through some unexpected quirks, I actually came not as an instructor, which is what the opening was for, but as a DuPont postdoctoral fellow. The department
Mhm.
had DuPont money that it could invest in any way it wanted, and I had an appointment with no responsibilities at all except to set up a lab and get some interesting chemistry going. And the promise was that after that first year, I would become an instructor and then go through the ranks as it worked out. So I came as an independent postdoc. Evenings I was still finishing the writing of my thesis. And in the lab, I could do anything I wanted, which was a terrific opportunity. One talks nowadays about startup money for faculty, and that's kind of interesting. The startup money for me, as explained by Professor Johnson, was you can take anything out of the stockroom you want, and you don't need to pay for it. So I had free access to the stockroom, period. And it turned out that was about all you needed to get going in those days. It's hugely different from how it is now.
Well, there were no big instruments that you absolutely had to have, I'm guessing. Right?
We had an infrared spectrophotometer, which was the main useful. It had ultraviolet. And they were really the only two physical methods available anyway.
So with your own two hands, you started doing chemistry on several different projects,
chemistry on some natural product structures, on some molecular rearrangements. Mike Carver has suggested that an amusing and accessible problem was to look at the active component in catnip. And there was a little bit of literature on catnip oil and how cats love it, and it seemed there was a simple 10-carbon compound whose structure had not been elucidated that the cats loved. And that was one of the things I worked on. It worked out very nicely.
So you could solve that structure just using infrared spectrophotometry?
One could solve that structure using a little bit of synthetic chemistry of degradation products and using infrared, and applying the isoprene rule, suggesting how the carbon atoms might be arranged. And that was a nice problem. And it worked out very well, and that was one of our early publications.
So when the news of the structure of catnip was announced, did you get inquiries? Was it something people picked up on at the time?
A little bit. There might have been a story in Chemical and Engineering News. Some of it was anticlimactic. I remember giving a seminar at Brookhaven National Lab on this great triumph of finishing catnip oil, and the culmination of the seminar was going to be somebody brought in a cat, and I was going to show the cat's response to this stuff. It turns out not all cats respond. It's a genetic trait that some of them have and some of them don't.
I see.
And I had a non-responding cat. So the chemistry was good, but I had not realized you have to pick your subject carefully.
Interesting. So you worked on rearrangements. I recall a really amazing rearrangement involving a carboxyl migration that you studied. You talked about it in your seminar at Cornell not too long ago.
Right. There was a rearrangement that I discovered actually reading the obituary of an old Swiss organic chemist. And he had found what seemed to be a very long-range migration of a methyl group when this cenenic acid was put into sulfuric acid. And I spent a lot of time being interested in molecular rearrangements because they play a very important role in structure determination at that time, where structures were determined mostly on the basis of chemical reactions rather than of physical spectroscopic properties. And so rearrangements were important, and here was this long-range methyl migration that made absolutely no sense. And it turned out if you looked at these structures, you could realize that you could come to the same final product structure without moving a methyl at all, but by moving a carboxyl group from one end of a molecule to another. And there's no reason why that would be easier, but it would have been a different mechanism, and maybe it would lead to understanding it. And we decided to study that rearrangement. And indeed, doing some C14 tracer experiments, we could show that this was a carboxyl migration for which there was no particular precedent. And we could work out the details of how that worked. And that was a really interesting mechanistic study.
So the first few years moved quickly, and you were successful in a range of different projects. I've noticed that from your early publication list. And then it must have been fairly soon after that you met Tom Eisner at Cornell?
So Tom Eisner arrived in Cornell, I think, in 1957. And we were introduced by a mutual friend who was Howard Schneiderman, who had somehow knew us both from Harvard. And when Tom Eisner came to Cornell, Schneiderman actually brought him around to my office and said, here's our youngest faculty member in entomology, and he does some interesting work involving insect chemistry, and maybe you can give him a hand now and then. And so I began to talk with Tom Eisner. We'd often have lunch over in the Statler, and he would tell me, in one lunch, he would tell me about a half dozen different insect stories that seemed to involve chemistry. I had a hard job keeping these stories distinct one from the other. And some of them clearly involved chemistry that you could approach and it would be fun to do, and some involved maybe high polymers, and I didn't know quite how to work on those problems. So I could sort of select a subset of the things that Tom was telling me and that he was excited about.
So he'd been going in and out of the field, bringing back insects and studying their behavior? Or?
That's right. So he knew a lot of natural history. So he knew the lives of insects in great detail. And he had a talent for bringing these insects into the lab, and if they had behaviors that involved chemistry, he would be able to dissect out the glands that contain the active chemicals, and then he didn't know where to go from there.
Yeah.
On the other hand, if he brought over a little glass vial and said, here's some stuff that has interesting biological activity, can you figure out what it is? That was just the sort of problem that
would be like an impedolactone story.
Yeah, that's right. And the nice thing about it is that lots of people work on plant alkaloids or plant aromatic compounds or drugs of one sort or another, but at that time practically nobody was interested in insects as chemists, and or in plants doing chemistry relevant to insects. And it turns out that that's a pretty fruitful area for organic chemists. And it had the great virtue that we could work on these problems and it wasn't hotly competitive.
You had that field to your own.
You could just quietly do it, you had it to yourself. Nobody even knew there were such problems, but when they were done, you could tell about them, and usually they made very interesting stories.
Gosh, there are so many of those stories in your collaborations with Tom. I remember you worked on the whip scorpion and the bombardier beetle.
Right,
Any in particular that are fun to talk about today?
Yeah. Well, the whip scorpion is a fearful-looking beast, but it's not a stinging scorpion. And actually, it's very interesting. That's the very first thing we worked on. They live in Arizona and Texas, sort of in desert areas. They're called vinegaroons in some places. And indeed, they smell like vinegar. They have a secretion that they can aim at an enemy that attacks them and spray an enemy with. It repels enemies, and it takes an afternoon to discover that the secretion is 85% acetic acid. And one isn't going to become a famous chemist based on finding acetic acid. On the other hand, it turns out there's about 5% of a minor component, which is an 8-carbon acid, caprylic acid, which is vital to the functioning of the acetic acid. It helps the acetic acid penetrate the cuticle of attacking insects, and the acetic acid then goes right through the cuticle and becomes a lethal weapon. And what we discovered in doing that work is that even if now caprylic acid is not a very complicated chemical either, but what you realize is that the application of these simple materials to important biological functions doesn't depend on them having sophisticated structures. That you can mobilize very simple materials, and they might be benzoquinones, or they might be benzaldehyde, or they might be rather simple things that you could detect quickly, which are vastly useful for the survival of the species that produce them. And so we began more and more studying mainly defensive chemistry. 80 or 90% of the time it would be routine chemically, but made an interesting biological story. 10 or 20% of the time they really were challenging structures, and it was interesting to work out the structures, to work out the biosynthetic pathways. How did the insects come by these chemicals? And after a while one gets an overall picture of the insect world sort of being very sophisticated, using organic chemistry to move their lives forward.
So when you and Tom would be together, how would you decide when to move on to the next species or when to look at some different question? Because I know you worked a lot also on butterflies and then soon on the interaction of insects and
Right. So
plants.
I usually relied on Tom to select what problems to work on.
Mm-hmm.
You know, there's something like 1 million described species of insects, and so you can't work on random ones. And one of Tom's great talents was recognizing when an insect seemed to be having some really unusual behavior that depended on chemistry or some unusual dependence on a particular plant. And so then we would focus on these outstanding things. And again, whereas many researchers took quite different approaches, like they would say locusts are a very important pest and let's study locusts, we didn't have that approach at all.
Mm-hmm.
We had an approach of, here are some interesting phenomena that I've observed in nature and what's going on. So at one point he discovered that there was some very interesting interactions in a tropical butterfly living in Trinidad, where it was well known at the time, just becoming well known, that many female moths can attract males by giving off tiny amounts of an attractive chemical, and males would come to them.
Mm-hmm.
What there were no examples, so females signaling males was becoming a well-known phenomenon.
Mm-hmm.
What there were no examples of is males doing any chemistry that's of interest to females. But it turns out in these tropical butterflies, which incidentally females don't use sex attractants, females appear, males have good vision. They see females, they fly to them from the visual
Sure, they're very brightly colored.
And that's right. And then it turns out that in these Trinidad butterflies, the males have particular courtship organs that they can avert from the tip of their abdomen. They brush across the female antennae in flight, and the females respond by alighting on some greenery and allow the males to approach them and mate with them. And so we looked into the male signaling system. What is the male telling the female that gets her to be interested in mating? And that turned out to be a really interesting story that we studied for about 20 years, going from one species to another and picking apart the different details of the process. And so first thing we did is we found the structure of the signal chemical that the female responds to, that the male gives her. And the structure looked like nothing ever seen from any animal at all. It looked like a plant alkaloid. And what we finally realized by studying related butterflies in East Africa, where I had an opportunity to work, we discovered that indeed this thing looks like an alkaloid because the butterfly, the African analog of this butterfly, makes it from an alkaloid.
I see.
And we
From a
discovered
plant alkaloid?
From a plant
Okay.
alkaloid. So we discovered these, they're called the African monarch. The African monarch flies out in nature, seeks particular plants, sucks in the juices of the senescent plants. They contain an alkaloid called lycopsamine, modifies the lycopsamine, makes the synthetic male pheromone, and that's what the females respond to. And we tried hard to understand, how could life be so complicated? How could the reproduction of this insect depend on the male going out, doing his sort of ethnobotany and finding
and then
useful
semi-synthesis
things,
after
and then
that.
metabolizing and signaling the female? How could reproduction depend on all that? And what we finally discovered is that this is a really wonderfully sensible system, and what is really going on is that the males gather these toxic alkaloids from plants. When they mate with the females, they transmit the intact alkaloid along with sperm. The females put this alkaloid into their eggs, and the eggs become inedible to predators.
I see.
And the female is essentially questioning the male in courtship to say, have you got the alkaloid to protect our children? And the male has to let her know. So courtship of these butterflies takes about 10 seconds. In this 10 seconds, he tells her, I am a good father for our offspring because I bear the protective compounds.
Right.
And he does that, by giving her the chemical that's made from the alkaloid.
It's
So
a kind
like
of
a
a gift.
certified check.
Yeah.
He said,
Or a
good-
dowry almost.
Right.
Yeah.
So I'm going to be a good father, and here's the evidence. And when she sees the evidence, then she's happy to have him as a mate. If he doesn't have that signal, she flies away from him. So that's a very interesting interaction between insects and other insects, between insects and plants, which nobody suspected anything like that is going on. And it turns out it's not unique. We have then found examples of similar strategies in beetles and in all sorts of ways.
So the clue must have come from finding this in the eggs, perhaps.
Well, the clue was, on the one hand, finding that the eggs are chemically protected if the female has mated with a well-endowed male, and the chemical similarity of the pheromone structure and the alkaloid structure gave the first chemical clue that there is a connection.
Wow.
Yeah.
So,
So
butterflies taught us about plant-insect interactions in part, and about nuptial gifts.
Right. Yeah, Tom was wonderful at making up names for these phenomena. Right, so he would talk about nuptial gifts, and that's a good, useful term.
It's a very descriptive term.
Yeah.
So later in your career, you also got interested in spiders. In fact, fairly recently.
Right. So, well, spiders are very interesting creatures. There's something like, 40,000 described species of spider, and they're presumably all characterized by being able to paralyze their prey.
Yeah.
So they make neuroactive compounds that one might want to learn about. And it turns out there are hundreds of papers looking at spider metabolites. Many of them looked mainly at proteins or peptide derivatives and at larger molecules. We began looking at spiders actually because a small company called Cambridge Neurosciences had come to see me and said, we have a spider-derived compound that might be an interesting pharmaceutical product if we could discover its structure. And they said, well, if we gave you the spider secretion and if we supported one research person, would you be interested in doing that? And that sounded quite intriguing. And we worked for over a year on the structure of the material that Cambridge Neuroscience gave us. And it worked out interestingly. We were very slow in figuring out what it was because it was a compound which was, again, unprecedented in nature. So it involved a nucleic acid base and a sugar, and they were sulfated sugars. And no one had seen anything like that from spiders or anywhere else.
This was HF7, if I remember correctly.
The company had called it HF7, and so it took us a while, but we finally figured out the structure of HF7. And just about that time, Cambridge Neuroscience looked at that structure and said, oh, that's too complicated. We're not going to make a drug out of that. They completely lost interest. On the other hand, we were quite intrigued, having found something new.
Sure.
And so we began we looked at over 70 different spider secretions, venoms, to see were there more compounds like that and to be able to exploit their biology. And as you well know, you and I actually collaborated.
Yeah, we did. That was a great
work.
joint project we had.
Yeah, it was a very nice project. And it turns out about 10% of the spiders we looked at have these sulfated toxin components, whose chemistry we still don't know too much about, and whose biology we know almost nothing about. And that's still a field for fruitful research.
I remember there were other spider constituents. Some were polyamine based that I had gotten interested in, and Merck was quite interested in many of those compounds.
That's right.
So I'm sure a lot of what you did was of interest to industry. You must have had some other interesting industrial interactions in your career.
Actually, I had very interesting consulting connections to industry, which went back to very early in my career. And I think if I boiled out all of the consulting experience, its main value was what I learned from it, rather than from what I was able to teach the companies. But I got into that in an interesting way. When I'd been at Cornell maybe about 3 or 4 years, it occurred to me that here I am in a great department at a great university, but of course one doesn't expect to be able to get tenure in a job like this. And it would be prudent if I learned something about the pharmaceutical industry, where lots of really good chemistry goes on.
So we're back in the 50s
And
now.
it's back in the 50s. And so I wrote Merck and Squibb and Cyanamid and Schering and a bunch of companies, literally Searle in Chicago, and said, you know, in the summer I'm uncommitted, and I could imagine spending a summer doing research in your lab if you would welcome an academic visitor. And we could maybe both benefit from that. And most companies wrote back and said, no, that really wouldn't make great sense to have an outsider becoming privy to all our results and whatnot. But one company, Schering in New Jersey, Schering Corporation, said, yeah, why don't you come talk to us? I spent a day visiting Schering. The research director was a man called E.B. Hirschberg, whose name I knew, who was a student of Louis Fieser.
Yeah.
And at the end of the day, I came to see E.B., and he said, well, you know, my colleagues enjoyed talking with you, but a summer job wouldn't make any sense. But how would you like to be a consultant for us? And we will pay you $200 a day, which at that time,
A substantial amount
my
of money.
annual stipend was $3,600. And so $200 a day is not bad at all.
Yeah.
And, you know, you come 4 or 6 times a year, and you can consult with us. At that time, Schering had only one other consultant that they hired recently, who was Derek Barton from London.
Yeah.
And so Derek Barton and I became the Schering chemical consultants. That connection went on for about 40 or 45 years, and it was really interesting. So I would go, and they were very involved in steroid chemistry at the time, and I would talk to the individual chemists, and we would work out how their steroid chemistry was doing. And I learned an awful lot of steroid chemistry, and now and then you do think of something that they haven't thought of.
You
And
might
now
have
and
seen
then-
a paper they've missed. Or,
Right, yeah, so you call their attention to this or that. And that was a really good experience, and I really did learn a lot from that industrial relationship.
Was it a conduit for students and postdocs to jobs?
Indeed. So, well, in general, it informs even one's teaching, because you can bring some practical examples of organic chemistry in action in your elementary organic classes. But also, when I came out of Harvard, I knew nothing about industry at all, but by virtue of that connection, I could sort of tell them what young chemists do when they go into industry, and what things they want, what talents they want to cultivate if they want to be good at it. And I could also tell them, were they likely to enjoy a pharmaceutical job, or would it be frustrating? Would they be able to understand that we'll work really hard on the synthesis, but if it turns out this compound has some neurotoxicity or God knows what, the project's going to be dropped like that, and you have to want to drop it. You have to say, well, too bad, the chemistry was going well, but this is not going to be a drug. I want to start my next project because my job is to discover drugs. And if that would be too frustrating, you're going to be very unhappy in work or sharing, because those things happen all the time.
So you enjoyed your time over that long stretch of consulting?
Oh
with
yes,
Schering.
I enjoyed it very much. And
Ashid Ganguly was director of research for a long time at Schering.
That's
and
right. Yeah,
you two became pretty good friends, I
right.
think.
He had been a postdoc, in fact, with Derek Barton. Barton sent a lot of his very best people to Schering, and they were really good chemists by and large. And so one got to know some very good people. Some of the time, my job was essentially to be a translator, because Barton was an imposing figure. And the way we would consult is that he and I would be sitting at a table, and opposite us would be the synthetic chemists. And E.B. Hirschberg would be sitting there. And they were supposed to get up and explain their problems. And under those circumstances, it's very scary for the chemists.
I'm sure.
So they would describe in as favorable terms as they could what their results were and what was troubling them. And Barton would sometimes just say a sentence or two directing them to something in the literature, and they might not catch the remark at all. And so it wasn't enormously helpful. The following day I would see these chemists one-on-one, and they would say, what is it Barton was referring to, because they were embarrassed to ask, especially in front of their boss.
Sure, yeah.
And I would say, well, what Barton was saying is this and that, and this is what he meant, and this is where you should go to look it up. And so I was sort of explicating the master's advice, which the chemists found really useful.
Yeah,
And yeah, so that was one of my roles. Is I was also learning from Barton, but sometimes I got the clue more quickly than they did.
Now, you talked a little bit about going to Africa, to East Africa, and I know you spent some time working on a project with Koji Nakanishi.
Right, so there was a time,
on insects.
I guess in the mid-1960s, or late 60s, when Carl Djerassi at Stanford got interested in chemistry related to insects, and had realized that there was a newly discovered compound, juvenile hormone, that actually controls the metamorphosis of insects. And Djerassi realized that insects are very exciting things, and had conceived of the idea that maybe one could start a research lab in Africa somewhere where insects were plentiful, and where one could do a lot of basic research on insect chemistry, which might directly or indirectly help his new company, which was called Zoicon.
Right.
And so he got a few people that he knew, biologists and chemists, to see would they be interested in starting up a research lab in Nairobi. Nairobi is a very cosmopolitan city in Kenya, and looked like it's English speaking, aside from Swahili, which is an East African language, but it had been a British colony. And Nairobi, most people who go on safaris start out going to Nairobi, and they have a base there, and then
branch
look at the
out,
rest of Africa. And Koji and I were the two organic chemists that Carl got to go out there. And the pattern was, why don't we take postdoc candidates who we thought would be good in this sort of semi-independent position, and set them up in Nairobi to do insect-related research and see what we could accomplish in a collaborative way. And we got support from United Nations. United Nations contributed a lot of money. Some companies gave money. And we had the directors of the lab were all representatives of the National Science Academies of US, of Denmark, Sweden, Holland, France, Germany. Max Planck Society gave some support. We got very good international support, a very impressive board of directors. And so our task as leaders of groups there was just to find interesting chemistry that one could discover studying African insects. So Koji and I both did that, and we would go to Nairobi a few times a year. We had some very good postdocs. One that I had was Glenn Prestwich.
Sure.
Very distinguished career after
Glenn,
that. And these postdocs lived in a way that postdocs don't normally live. That's how their postdoc stipend. They could rent a nice apartment. They could have a houseboy who did all their shopping and cooking for them. They lived in glorious sort of colonial style. And they could concentrate on their chemistry. It was a wonderful experience for them. And we worked a lot on termites. It turned out termites are very interesting chemists. And we worked on these African butterflies, which were very important for us. We had great fun doing that. The idea of the lab was initially that it would have foreign research directors, such as we were, but that in the long run we would phase ourselves out and we would appoint African research directors as they appeared on the scene. And that lab, which is called ICIPI, still exists. It has now a few hundred researchers. It's a great center in Nairobi if someone wants to spend a sabbatical leave and have access to good mass spectrometry and NMR spectrometry and all those things. And it's gone a little bit more from basic research to applied research, but it's applied to problems that are important and useful in Africa.
So was the Institute successful in training African scientists or recruiting African scientists?
It trained African scientists who then go back to their universities. The director of it was a really interesting man called Tom Odhiambo.
Oh, yes.
And Tom Odhiambo had been a student of Sir Vincent Wigglesworth, who was the father of insect physiology in Cambridge. And Wigglesworth declared Odiambo to be his best student ever. Highly, highly productive. And he was a young, I think he was a lecturer in University of Nairobi when he and Gerasi really organized this lab. And he directed that lab for many, many years. A highly articulate man. He spoke better English than any of us with this sort of British education.
Right.
Who was very good at raising money. He gave wonderful talks and attracted a lot of support. And so that was an interesting experience. In fact, the sculpture behind you is a Conde sculpture that one of many that I would buy when I would be in that area of the country.
Sounds like this was a hugely successful experiment.
It was a successful experiment and an enjoyable experiment. It produced real science and contributed to the development of chemistry and biology in Africa.
Was Tom Eisner involved in any way? Or?
Tom Eisner was not. You know, one of the interesting things about Tom Eisner is that he didn't get on airplanes.
Right.
And when he would go on sabbatical leave to Europe or even to Australia, he did that by ship.
Right.
But he was not about to sail back and forth to Africa.
Right.
He mainly stayed in Ithaca all the time. So we did that. If we had had Tom Eisner in Nairobi, the lab would have been even more successful than it was by quite a bit. But no, he was not involved there.
So more recently, you've been involved in an institute being planned for Brazil. Is that right?
Very interestingly, so Koji and I became great friends and collaborators through that African experience. And about 20 years after we had done that, that was the late 60s and early 70s, maybe about in the early 90s, Koji had a friend in New Jersey who was a Japanese Brazilian. He was a person who had grown up in Sao Paulo from a Japanese family, went to Caltech as an undergrad. His name was Dr. Yamane. And then Yamane went to Bell Labs, had a nice research career in Bell Labs, and then retired a bit early and wanted to go back to Brazil and bring some more contemporary chemistry to the Brazilian scene. And since he and Koji had somehow become good friends, he asked Koji could he help him set up a research center in Sao Paulo to study natural products. And since Koji and I had worked together, Koji said, would I join him in that endeavor? And there looked like a great opportunity. And so Koji and I began thinking about how to organize a lab in Brazil. And its main purpose would be to look at the Amazonian region as chemists and see what could we do with Amazonian plants and animals that would be scientifically interesting and also useful.
And timely, before any further destruction of that region takes place.
Indeed.
Huh? Yeah.
Well, and so we began doing that. I organized a meeting at the American Academy of Arts and Sciences. We brought in some Brazilian scientists and Japanese and Europeans and Americans. Tom Eisner participated in that. You know, Tom Eisner sort of grew up in South America.
Yeah, he did.
In Uruguay. And we talked about the potential of starting a lab, something like this African lab, maybe in Manaus, which is in the heart of the Amazon. And indeed, we talked about it. We planned to organize it. The Brazilian federal government, to our amazement, committed much more money than we had expected to set up such a lab. But ultimately, that was about maybe 15 years ago or so. It turned out it's much harder, at least for us, it was much harder to establish a functioning lab in Brazil than it had been in Africa. So our experience in Kenya was really quite good. And I think because Kenya had been a British colony, it was set up in a way that Americans could understand the ethos very,
Right.
very well. Brazil has, of course, not been a British colony. It has its own style,
Yeah.
and none of us, neither Koji nor I nor the biologists who we were talking to, had South American experience at all. And whereas it looked very promising, it turns out we weren't really successful in navigating the system very well. And that lab, maybe now 15 years later, is just barely getting going. In fact, it's a little too late for Koji's career and mine.
Yeah.
And it's a little late for Brazil because the environment is being destroyed at a fearful rate.
Yeah.
Even when we were organizing it, we had the Secretary for Amazonian Affairs come to our initial meeting. And he talked about the Amazon region and explained that, well, it's being destroyed at a significant rate. And he showed us a map of the Amazon and superimposed the country of France.
Oh my
And
goodness.
they had already lost at that time an area equivalent to France
Wow.
of nature was
Yeah.
gone forever.
Through
And-
development, basically.
Right.
Yeah.
Just by
Yeah.
clear cutting and
Yeah.
selling the lumber and
Yeah.
whatnot,
Yeah.
or trying to do clear cutting and trying to do agriculture, but the land in a thoughtless way.
Mhm.
And it turns out the soil doesn't last very well when you cut down these forests.
Mhm.
You need to understand how to do things there much
Yeah,
better than
yeah,
was understood up to now. And so nature is disappearing,
Yeah.
species are being lost forever. One will never know what great natural products might be in the plants,
Yeah.
which are now going extinct. Someone described this as we're trying to look at nature's library, and nature's library is being destroyed
Yeah.
before anybody's read
Yeah.
any of the books.
Yeah.
Yeah. They're going away. So the pressures to work there are enormous, but it's a difficult organizational job, and we had not completely solved
Yeah.
it.
It's too bad because there's clearly the resources are there, even more so now than ever. The economy's booming, but if the system can't be established that works well.
It's very hard, and there's not the same entrepreneurial spirit. There's not
yeah.
the tradition of people investing in science with the feeling that a half dozen years
Mhm.
from now we'll find something that will
Yeah.
make money.
Yeah.
Because you can make money immediately
Sure.
by selling the
Yeah.
lumber.
Yeah.
And things need to change and need to be done in a more sophisticated way.
Mhm. Yeah. Jerry, we shouldn't leave today's conversation without talking about teaching some. You and I have had the pleasure of teaching organic chemistry together, but you've done far more than that. I don't know, where is a good place to start?
Right.
In the
well,
early days after you became a tenured faculty member, or more recently?
Yeah. Well,
You've created
always-
quite a few courses.
I've taught introductory organic
Yeah.
chemistry on and off for the entire 54 years that I've been teaching at Cornell, and somehow I find the subject just so beautiful and so intriguing that I still love to lecture on introductory organic chemistry. How do you figure out that carbon forms 4 bonds pointing to the corners of a tetrahedron? How that was done so long ago with no physical methods of determining structures of molecules. It's truly a wonderful story. And so I really always enjoyed teaching introductory organic chemistry. It's a beautiful subject. You have to somehow get people to be not afraid of it and not to just be taking it because they need an A to go to medical school. They might start with that motivation, but if they could realize that, what do you know, this is an intriguing subject and really quite beautiful and fun in its own right. So it's nice to teach sophomore organic chemistry and get that across. Once I started working with Tom Eisner, I began drawing in more and more biological examples to the teaching. And finally, Tom and I began teaching a course in chemical communication, where we would talk about how plants talk to each other, how bacteria talk to each other, how fungi talk to each other. We sort of broadened our own research interests to looking more broadly and to make a really nice introductory course on on the importance of chemical interactions in biology in general. And at the time we began teaching chemical ecology or chemical communication, I think there were very few courses like that.
Was it a graduate course?
It was. Well,
upper level
it was
course?
appropriate for seniors,
Yeah.
seniors or graduate students. Many of the people who took that have gone on into the academic systems throughout the country and are doing research of that sort and teaching of that sort, so that it's now a more widespread subject than it used to be. And that teaching is entirely different from teaching pre-meds, undergrad, organic, but both the graduate course and the undergrad course I always found very, very intriguing, very much fun to talk about.
Now, there was a time, we both remember, when we were looking to create some courses for non-scientists.
Right.
And you had a very popular course about chemical communication.
Well,
I think it was slightly different than the one you've just described.
Well, what occurred to me, sometimes socially, you'd be at a party with some colleagues, and colleagues in other fields, and so you always ask colleagues, well, what do you work on? What do you do? And so students would ask me, I'd say, well, I'm a chemistry professor. They'd say, well, what does a chemistry professor do? So I would tell them things like stories about butterfly courtship and how females select mates based on chemical signals. And what I realized is that you can explain to a government professor or an English professor in 10 or 15 minutes with a glass of sherry in your hand and no blackboard. You can tell that story in a way that he walks away amazed that that's what a chemistry is doing, is studying how male butterflies seduce females using chemistry. And it occurred to me that he then has an impression of chemistry quite different from he would have had before we had that glass of sherry together. And then I thought, why couldn't one do that in a class? Why couldn't you have a chemistry course with no prerequisite? You use non-technical terms, but you explain what the chemistry is, and then you go back and fill in the details so that the students could actually learn what is the underlying chemistry, how do you solve this problem, and you would end up with students with some appreciation of one area where chemistry is contributing to biology, or in some instances how some medicine was developed, or how some other useful material was developed. You could actually teach that if you would be patient enough and give students a picture of chemistry entirely different than they normally would have. Right, so we found that we started a course doing that, which worked quite well.
It was extremely popular.
It worked quite well, and recently I edited a book for the American Academy of Arts and Sciences with a colleague, John Hildebrand, who's a good friend of Tom Eisner's in Arizona, where we looked at what are novel ways of teaching science, and our approach is one. There are other ways you can approach bringing non-scientists into the field of science and getting them to understand it without a math background, without chemical prerequisites, and that would be a useful way of bringing our students who are just liberal arts majors, not in science, bringing them a little bit into our world. Yeah, so that was also an enjoyable teaching endeavor, which worked out well.
Yeah. Some of the stories, as I hear you talking about them, remind me of some of the talks you've given at National Organic Symposia and other big conferences. I don't think I know anyone else who's gone as a plenary speaker to so many different National Organic Symposia. And maybe you can tell us about that, but with talks that start with some basic research investigation that leads to something that could become a useful drug.
Yes. Well, one thing is that
is it 8 or 9 National Organic Symposia? But it's a large number.
Actually, I think it was 5. But
Okay.
but those are meetings that take place only in alternate years.
Right.
There are some years where I decline to give. The way the speakers are selected for that is that the membership of the ACS is polled. Who would you like to speak
You're
at
a
your
very
national
popular
symposium?
guy. Yeah.
And normally people give 1 or 2 talks of that sort in their career. But in fact, I would be asked year after year, and some years either I had a conflict of time or I thought I didn't really have enough new material to do it. But many times I did do it. And it's interesting because you can give talks that have real chemical content, but also that chemists can bring their wives, and their wives will get about as much out of the talk as the chemists themselves. And this is just a very fortunate subject that you can treat in that way. Many aspects of chemistry, you couldn't possibly give a lecture like that. Yeah, this sort of thing I realized early, that if your mother came to a lecture, she could understand that lecture and she could finally understand what you're doing.
Maybe not everyone could give such a talk, but you certainly give a spectacular talk that the general audience can appreciate. No one, I think, does it better than you, Jerry. So, you know, we should also talk about the various academies and your interactions with them. I know you were elected to the National Academy quite early in your career, and I've mentioned also the American Academy and the American Philosophical Society, and you've been quite active in those groups. Tell us about that.
Tom and I were both elected to the National Academy in 1969, so Tom was 40, I guess. I was 42. That's fairly young. And at the time, I think we regarded that as mainly a great honor, a very prestigious thing. We weren't really thinking about what the Academy actually does. The National Academy actually was founded in the time of the Civil War, and its purpose was to provide unbiased expert advice to the government. And that's still the purpose of the National Academy of Sciences. So it undertakes, if the government wants to know, say, about the role of pesticides in the environment. Is that becoming problematic? How should we treat that? It will ask the Academy to put together a committee to do a serious study of how pesticides are involved in the environment. What should we do to promote the beneficial use of pesticides or to prevent the use of difficult ones or whatever? And there'll be a year or two study by an expert committee. It'll report to the government, and the government will presumably rely on that to direct policy. Anyway, that's its
those were the days.
That's its official role, and those were the days when it did it. But mainly, so in part there's a serious purpose and there's an honor. The Academy also publishes the Proceedings of the National Academy, which is a major prestigious scientific journal over all fields. And I think so when we were elected to the National Academy, we thought, isn't that terrific? Neither of us did very much about it. But then Tom became very involved. The Academy is concerned with human rights very much. And Tom became very involved in things where there are human rights violations against scientists worldwide. I'm now on the editorial board of Proceedings of the National Academy, and I'm trying to build up its publication record in chemical ecology, which is sort of an orphan field. It's not yet in the center of our subject, but there's beautiful work going on, and when I get good papers submitted, I can guide them through the editorial process and help them appear. So in recent times, I've been quite involved with the Academy, although I wasn't before.
Yeah, you have more time now.
And I have more time.
Easier to be away.
It's a very good thing to do when one is officially retired. In the American Academy of Arts and Sciences, somehow I evolved into being secretary of the Academy. That was an academy founded by John Adams. It's much older than the National Academy, and its purpose was to promote useful knowledge. And again, it's a great honor to be elected to it, but besides the honor, it does things. The American Academy has a broader range of subject matter, so it's arts and sciences. It has members in all fields. It doesn't wait for the government to ask. It has no government connection. It doesn't wait for the government to say, we'd like to know something about this subject. Its members think about what are important national problems and what problems would benefit from interdisciplinary studies of what that problem is, be it weapons in space, or be it protection of the internet, or be it the fate of humanities in United States education. So it initiates its own studies, it puts together interdisciplinary groups, and those studies are then published and widely distributed. And there's been a very recent study on research policy in the United States with respect to especially health-related research. It had a committee headed by Tom Cech, who is a Nobel laureate on NIH support of health research. And it did discover some really interesting things. It turns out that the average age when an independent investigator gets his first grant from NIH is 42 years old.
Sure.
That's practically halfway through one's career. And if you've got to wait till you're 42 to get your first independent research grant, that's too late. And so the study that came out wasn't a plea for more money, but for more intelligent use of the money that we've got. And it said, you know, you've got to not just support research that's sort of a sure thing where there's 5 years of results and now I'm going to pursue that, but where there's a really brilliant idea and no results at all perhaps, but let's give it a shot. And maybe this idea is from a 28-year-old investigator. Let's put money into that. And the NIH indeed has begun much more supporting young people as a result of that study. This study has been really influential. And they had started some programs for young investigators. They had done one, and it turns out there was so much pressure on the system that the funding available was 1% of what was applied for. And again, this report pointed out it's stupid to have a program where you ask for great proposals from young people, you get all these great proposals, you involve so much time refereeing those proposals, bringing them to study sections, debating them, and then in the end you support 1%. Nothing comes out of that. So if you start a program, you have to be sure you have the funding to go with it. And so all of those things are having a real influence, and all the American Academy reports aren't that successful, but that one is having a great influence, and there's the potential for really helping guide academic research in the U.S.
Well, honestly, Jerry, anyone who knows you would know that this would be a natural fit for the sorts of interests you've had. I will always remember after my Cornell interview in 1973 that you showed up in San Francisco. We had planned, you were going to be there, and we had dinner together, a dinner that was extremely influential in my decision to come here. And I also remember that you just casually mentioned that night at dinner that you had bought tickets for a concert at the Fillmore West, which was a place for the loudest, most boisterous music of my generation, and I was just astonished by that. And then again, hearing that you'd gone to the Fillmore East in New York City to, I guess it was Bill Graham's Fillmore East, to hear some of the latest rock bands of that era. So you had a profound influence on me in the sense that you could do great things in science and still have these amazingly broad interests in music, and so that it's a natural fit for this report that you would have helped commission to do that. So we didn't talk about the American Philosophical Society. Are there activities there that are of keen interest to chemists?
Well, there could be. The Philosophical Society actually was started by Benjamin Franklin. It's slightly older than the American Academy. And again, Franklin's idea was to get a bunch of his buddies together in Philadelphia and talk about what were going to be the needs of this new country, and how could they help advance the country by studying agriculture or medicine or business or whatever that would help things flourish. They also referred to useful knowledge. The American Academy has a continuous history since then. of the Philosophical Society. And in part, it's almost a subset of the National Academy.
I see.
It has something like 700 members, therefore it's more club-like.
Yeah.
It has distinguished national membership and also quite a few foreign members. It has meetings twice a year. I was elected, I think, in the mid-1980s. I was confused at first. There seemed to be very few philosophers who were members of it, but it turns out that what Franklin meant by philosophy was natural philosophy. It was really science.
Right.
But it has, again, a broad membership now. It tends to elect people who've been active and productive in whatever their fields are. What I've mainly enjoyed there is I'm on the membership committee, on the program committee.
Yeah.
And what's great fun is selecting people who will give really informed talks and really teach us something about a subject that we'd like to know about and what we think is important. And the program committee has about 15 members, so there's expertise in a lot of fields. The talks are very unusual. People are invited to give a 20-minute talk, which is not easy.
Yeah.
20-minute talk.
It's like 5 slides almost.
You have to really prepare it very carefully to teach the audience a little bit about what this field is about, to have some context, then what interesting thing you want to tell them in that field of your own work or of other contemporary work, and then sum it up so they go away with the message. People prepare those talks very, very carefully, and they inform us in interesting ways. We do get awfully good people. So once there was supposed to be a talk by a young lawyer who was, I forget what he was going to talk about, but it turned out he couldn't come because he was being drafted to help write a constitution for Iraq. And he was a young professor at NYU. And so he had clerked for Judge David Souter. And since he couldn't give the talk on Iraq, David Souter came to read his paper. And so that's the quality of speaker we would get. Souter did a wonderful job of reading his clerk's paper. He ran a little overtime, and when you run overtime, a little red light comes on to stop you. And when the little red light came on and Souter hadn't quite finished the paper, he took out his handkerchief, covered up the red light, and finished his talk.
That's a marvelous story.
So that group it's great fun.
Yeah.
It also has a research program. It supports young investigators. It supports field research, even by graduate students. It turns out it's very hard to get research for young biologists to go out in the field and do their studies. It costs almost nothing. You know, hundreds of dollars or a few $1,000s will get a grad student to spend, say, a month in Ecuador and discover all kinds of great things. And the Philosophical Society supports a lot of that. I review a lot of those grant proposals, and you read these intriguing proposals where, for modest sums, you can do exploratory things in areas which are not in the forefront of medicine or whatnot right now, but are in the forefront of some field of knowledge. And the Philosophical Society has a wonderful library. It has things like all the Lewis and Clark papers and all the things related to that. People come from all over to use their research library. And so its main scholarly activities are the library and support of research among very young investigators, and it has these wonderful meetings.
There must be some philanthropy that backs up the society.
And it is,
They get gifts and
they
so
get
forth,
gifts from foundations, they get gifts from members who have a great time going and often leave their money. In fact, it's really interesting. The Philosophical Society has an endowment, and say in a couple of weeks we'll be going to the fall meeting. If you get yourself to Philadelphia, they put you up in the hotel, they feed you the meals during the meeting, they host you completely, so you're the guest of the society. The National Academy, and it has no dues, it's presented to you. So it's great fun, those meetings. The National Academy has a party or two but charges you for them when they have a meeting. It has no dues. It's well enough endowed, and it makes money from the government studies because the government pays for the studies.
Yeah.
The American Academy of Arts and Sciences is not as well endowed, does not get big grants from the government typically, and therefore it costs something like $300 a year to stay a member of it. So they're economically, I think they're quite jealous of the Philosophical Society. But all of them need support. All of them get support from faithful members, and that helps them function.
So it's coming up on 60 years at Cornell. A long time to stay in one place. There was a time you left Cornell for a short time.
There was a time after I'd been here 20 years, and things had been going along very well, and the work with Tom Eisner had gone very well. And as you well know, one gets offers from other institutions now and then to come and join their faculty. And there was at one point an offer from the University of California in San Diego in La Jolla. And La Jolla is sort of paradise on earth. And they're also associated with the Scripps Oceanographic Institution, which is one of the world's great oceanographic laboratories. And I spent a little time there as a visiting professor, and it looked to me as if the world of terrestrial biology was going along quite well, and we knew a lot about insects and plants, but that the world of marine biology was very obscure, very exotic, these strange-looking creatures, and producing odd organic chemicals, all kinds of halogenated compounds and exotic structures. Some of them were potential drugs. One knew nothing about their actual role within the lives of the organisms producing them. And it seemed to me that if I would accept the offer in La Jolla, one might begin to do the things in the marine environment that would be analogous to what we had done with insects and plants. And that would be a sort of new frontier. And so in 1972, I actually accepted a professorship there, and we sold our house and we bought a house in La Jolla and began to work there. And for complicated reasons, it was much less satisfying than working at Cornell. The Cornell chemistry department is really a seductively attractive place, right? It's very collegial, as you well know.
Absolutely. You had a lot of friends here when you left.
We had a lot of friends, both in chemistry and in music and in the university in general. It was a lovely environment. I missed that very much in UC San Diego, which was a young institution and feeling its way. It had a chemistry department originally with Linus Pauling and Harold Urey, Nobel laureates. It built itself with stars. And its philosophy was, we'll get these stars and they'll do beautiful work and we'll be a famous place. What it turns out doesn't work so well is if you import and depend upon people who already are prima donnas in their own place, that it's very hard to get a coherent department. There was a tendency for faculty in San Diego to set up a beautiful research lab, have no interest in the teaching and no interest in talking to their colleagues. It was very, very insular. And in fact, a lot of the things that were important at Cornell, like teaching, graduate teaching or undergraduate teaching.
And talking to your colleagues.
And talking to your colleagues didn't go on or went on not very well. And the Cornell chemistry department depended a lot for its growth on getting the brightest young assistant professors and trying to help their careers develop as say your career or my career developed. And if you grow up within the department, you have a kind of commitment to it and a feeling for it that you don't necessarily have if you were already a famous person at Chicago or Columbia or Caltech. Then you come here and you just want to continue being the famous person you were. And the Cornell department actually is able to do both. As we can recruit a star now and then, and they will fit into the culture that's already here and do very, very nicely. But to have the department depend entirely on those outside people, I think it doesn't work. It wasn't working in La Jolla, and in fact it was so unsatisfactory that we only stayed there a year, and to my great good luck, Cornell hadn't replaced me yet. And in fact, officially, I was on leave because I brought 8 students with me, 8 Cornell students, moved to San Diego, and began working with me there, and I wanted to stay on their committee. So on paper, I was on leave, although I had told the chair and the president that, this is a permanent job and I've accepted it.
How did those students feel about coming back to Winter in Ithaca?
They were delighted. Well, 2 of them finished, got their degrees, got jobs. 6 came back. They convinced a couple of the San Diego students it's much better at Cornell than it is in California. So a few California students came back with them. They had a wonderful sort of sabbatical leave, and they enjoyed it. They could do tennis all year round, or golf, or surfing, as well as chemistry. Enjoy the good weather. But they were happy to come back. My family was happy to come back. And I was happy to come back.
And we were thrilled that you came back. So that was mutually a perfect solution. So looking back, since that time, another 30 or 40 years, I guess, at Cornell, what other changes have you noticed? I think the collegiality is something we still have, but it is getting harder to find time to talk to your colleagues. The internet makes life pretty insular now. You can just stay in your office and get everything you need. There's no physical sciences library.
Yes, there's no doubt that many things have changed. I guess when I came here, the chemistry department was in Baker Laboratory, and that was the only place it was.
There was no Olin lab.
There was. So I was on the building committee for Olin, for SD Olin, and that sort of doubled our research space. The research space is wonderful. The offices we have are lovely. It was fun being on that committee. The original proposal was to build a lab with no windows. And I remember we objected, Bill Miller, who was chair of the committee, saying we're not going to build a lab in Ithaca in these beautiful surroundings and not have any windows. We actually got the administration to change architects and build us a lab that we can be really proud of and comfortable in. As you well know, chemistry professors essentially spend most of their life
we don't get out much.
Laboratory.
That's right.
It's quite different from our colleagues in humanistic studies. I mean, they come to their office for office hours and they give their courses, but the way they work, it doesn't really put them in the English building all the time.
Yeah, sometimes they teach on the arts quad on a nice day.
Yeah. So the life is different, and we got ourselves a beautiful building. Now we have still another building. And so chemistry is beginning to spread out. A problem in La Jolla was that chemistry was in 4 different buildings.
Wow.
And 4 different buildings, you don't interact with your colleagues very well. That's a thing I think we have to be aware of and worry about. We have to try very hard to keep seeing one another.
I agree.
Other social things have changed. It used to be a lot of chemists would eat lunch in the Statler Club and the faculty club. And I ate not only with Tom Eisner very often, but with chemical colleagues. And one could discuss informally lots of things that benefited from informal discussion.
And seminars were typically followed by a social hour.
Right, so attendance at seminars has changed. The problem is that chemistry has spread its wings. So there was a time when you could go to almost any chemistry seminar and understand it. That's not so easy now. There are seminars that I look at the title of and I don't even understand from the title what this seminar is going to be about.
Me too.
And if I go to that talk, in the first 5 or 10 minutes, I gain something from it, if the lecture is good. But then it gets into areas that I don't know the vocabulary for. And I can't really understand that talk anymore. And I think many of us experience that.
Yeah, it's discouraging.
seminars become much more specialized. We don't have a common audience, and that's sort of discouraging. If you have a seminar where all the faculty goes also, then all the grad students tend to go. If their professors aren't going, they're not going to go. And that's a problem not of Cornell, but
that's a problem of our field.
Of our subject of the field.
Yeah.
I suspect other subjects may have very similar problems, that the subjects have got so broad and so powerful that you can only know a part of it. Coming back to Woodward considered himself not an organic chemist, but a chemist. And Woodward read really the inorganic literature, the physical literature. One of his great strengths is that he brought physical methods to be applied, infrared spectroscopy, NMR, whatever, mass spec. He brought them into his own field of expertise. Nowadays we can't read the literature in all the fields because there's too much of it.
We can barely read our own literature.
We can barely read our own literature. And so the subject is changing.
And chemical ecology, this field you and Tom more or less gave birth to here at Cornell. We've seen it develop. Many great students of both of yours, you and Tom and others, have started to work independently. What do you see as the future of chemical ecology?
Well, chemical ecology is going to blossom and become more and more important. Because in fact, whereas in the beginning we ourselves were just studying insect things or spider things or plant-insect relations, and there's a Society of Chemical Ecology where maybe 50% of its work is in those areas. But what's become absolutely clear now is that all organisms use chemistry for communicating. So bacteria have a phenomenon called quorum sensing, where they can estimate what their populations are, and they can change their behavior when the population builds up to a certain number. There are organisms called slime molds, which are essentially little amoeba, one-celled organisms. When slime molds use up a lot of the food in their area, they suddenly attract one another, form a little worm-like slug, which actually moves away and looks for food. When it finds food, it develops another sort of structure and forms spores which disperse and
that's amazing.
Explore new areas. And so all of these things are talking to each other with chemical signals. Just about 2 days ago, I heard a wonderful lecture by a gal, Bonnie Bassler, at Princeton, who studies bacterial behavior and quorum sensing. And interestingly enough, Bonnie Bassler is a biologist and needs chemistry to understand what her bacteria are saying to each other. The chemist she works with is Martin Semmelhack. Martin Semmelhack was a Cornell chemistry professor who we lost ultimately to Princeton. And now he studied really synthetic chromium chemistry and whatnot, and synthetic methods. But she has him now studying how bacteria talk to one another. And these fields are going to be very important because they control things like when bacteria become pathogenic and how they do that. How they form biofilms and change
and adhere to things,
And so bacteria are doing it, fungi are doing it, algae are doing it, everybody is speaking chemistry. And so chemical ecology, which is essentially just the study of those fields, is automatically going to grow. Marine chemical biology that I mentioned before is hard to study because you have organisms that live, say, a mile deep, and you bring them up to the surface, they explode. It's not so easy to study behavior of organisms like that. But nevertheless, something like 2/3 of the Earth is covered by oceans. Most of the photosynthesis on Earth is in the ocean and not on land. We need to understand those organisms, and ultimately we're going to depend on them a lot. And that's a beautiful field, but interestingly, it's hard to get support for the research. It's hard for individuals to pursue it because you need to know not only all the relevant biology, but you need to bring the chemical tools. those are going to be studied by collaborative groups like the Eisner Meinwald group,
Mhm.
but maybe on a larger scale, and bringing different talents to the table. So I think it's going to become a hugely important subject, but it hasn't quite yet. I was involved helping the Max Planck Society found their first laboratory for chemical ecology,
In Jena.
which is in
Yeah.
Jena in the former Eastern Germany. The Jena lab is headed by Ian Baldwin, who's a Cornell PhD,
Mhm.
and that lab is now at the forefront of the subject. But there are not many labs like the Jena lab and like Cornell,
Mhm.
and its extension in Geneva, where Wendell Roelofs
Sure.
was a great
Right.
pioneer.
Yeah. Yeah.
Wendell Roelofs got into I actually recruited him for Cornell.
Mhm.
His training was in synthetic organic chemistry. He got to Geneva, and unlike Tom and me, he focused on important problems. and so he worked on crops and on pests and did wonderful things. There'll be labs for chemical ecology. They may not call themselves that,
Mhm.
but they will be developing and be of increasing interest as time goes on.
Mhm. Well, I mean, Cornell has certainly had its share of people. I think you inspired John Clardy to a significant extent when John moved here from Iowa State and then began looking at organisms, I think most recently deep subterranean organisms, and finding what interesting structures they produce by scanning large sections of their genome. And I don't know whether May Berenbaum had been a student at Cornell.
May Berenbaum was a Cornell PhD,
Yeah,
also
yeah.
a student of Paul Feeney's, and has become very influential in chemical ecology.
Mhm.
And she now chairs the entomology department at the University of Illinois.
And Joe Handelsman was a student at Cornell,
Right.
now at Wisconsin, doing
Indeed,
great
yeah.
things, I think. So.
Yeah, doing these very interesting things of getting DNA from the soil.
Right.
And even though you don't know what organism this DNA comes from, you can find out what
What the
chemistry is it
compounds
capable
are.
of
Yeah,
doing.
Yeah. So chemical ecology is in good shape.
So it's in good shape. It's alive and flourishing.
Well, I think that's probably a good point to wind things up. We've covered a lot of, as I had hoped, a lot of the highlights of your career, insights into some of the people you've known and trained, perspectives on where things are going. I've enjoyed this a lot, Jerry. It's been long overdue. We should have done this many months or even years ago, but I guess the longer that we've waited, we've included more and more perspectives. So thank you very much for taking the time to speak with me, and I hope that this will become a valuable contribution to Cornell's Oral History Project.
Well, thank you. It's been a great pleasure.